Polarization is a property of waves. Actually, it is a property of transverse waves only. There is no polarization for longitudinal waves. For example, I can use this spring to make transverse waves and make it oscillate in all kinds of directions. But this spring goes through the slot, vertical slots over there, and the slot only allows the spring to oscillate in the vertical direction. So the slot acts like a polarizer. So beyond the slot, on the other side of the slot, if I make a horizontal oscillation, there's no oscillation on the other side. If I make it a vertical, then the vertical oscillation can go through the slot. If I make a slanted wave, then the vertical component is the one that goes through. There's no polarization for longitudinal waves because a longitudinal wave would go through the slot no matter which way the slot is oriented. EM waves are transverse waves, so we can talk about polarization for EM waves. An EM wave has oscillating electric field and magnetic field. And we use the direction in which the electric field oscillates as the direction of the polarization. A beam of unpolarized light would have electric field oscillating in all directions perpendicular to the beam's velocity. There are a few different ways to polarize light. We will discuss two of them, by polarizer in this lesson and by reflection in the next lesson. An example of a polarizer is a sheet of Polaroid like this one. It is made of some sort of polymer with long-chain molecules. When it's made, it gets stretched so the long molecules line up in this direction. It is then dipped in an iodine solution, so the molecules can become good conductor along the long chain direction. When we shine an unpolarized light at the polarizer, the electric field oscillating in this direction gets absorbed by the electrons that can move along the chain. So only electric field oscillating in a direction that is perpendicular to the long chains can come out the other side. This is how I draw a polarizer with a transmission axis in this direction. And the light coming out the other side is polarized in the same direction. If the original unpolarized light has an intensity I0, the polarized light would have an intensity half of the I0. Because an unpolarized light has electric field in all directions. So half of its energy is in this direction electric field, and the other half of energy is in that direction electric field. As for a slanted electric field, we can just break it into components in these two directions. So when the unpolarized light from my lamps goes through this polarizer in the Y direction, only half of the intensity is left. So everything looks darker through the polarizer. Now I'm adding another polarizer that is also in the Y direction. All of the Y direction polarized light can go through the second polarizer. When the second polarizer is in the X direction, no light can go through because the Y direction electric field has no X component. I can rotate this second polarizer so you can see how the intensity of the light changes. Let's say that the second polarizer has an angle theta to the polarization direction. So only this component of the electric field can go through. To find the component that goes through, we can draw a rectangle like this. This angle here is theta. And the component we want is the adjacent side to the angle. So if this electric field is E, then the component we want is E times cosine theta. For EM waves, the electric field is like the amplitude. So the intensity is proportional to the amplitude squared. That means when the electric field changes by a factor of cosine theta, the intensity would change by a factor of cosine theta squared. Therefore, the intensity on this side is the intensity before times the cosine theta squared. And the intensity before is 1/2 I0. So when an unpolarized light goes through a polarizer, the intensity changes by a factor of 1/2. When a polarized light goes through a polarizer at a different angle, the intensity changes by a factor of cosine theta squared.